let's talk about the ratio test. So this is the beginning of section 8.4 in the book, and we're doing this instead of the reading this time. So I want to remind you, we are still trying to answer the same question that we've been answering the last few sections, which is, here's a series, does it converge or diverge? So we're going to add one more test to the list. So far we have those two comparison tests, we have the integral test, nth term test, and our next one up here is the ratio test. Alright, so what the ratio test starts with is, they give you a series, you're trying to decide if it converges or diverges, and the way that this is written here, we need the terms to be all positive numbers here, so all of the little ANs should be positive, and like we said, there's a section coming up that deals exclusively with the series that go positive then negative, and those are the real kind of troublemakers that don't fit here for now. Okay, so once you have a series like this, you're going to compute the limit as n approaches infinity of the n+1 term and then the nth term. So this bottom part here is exactly the formula you see in the series, and then the top one here is the same formula but with n+1 plugged in, or whatever your letter is plus 1 plugged in. So you're going to take the limit of the ratio of consecutive terms, and presumably it's going to come out to some number L. If this limit doesn't exist, you're already kind of out of luck, but let's assume that it comes out to a particular number L. So we have kind of rules for what values of L mean what. So the first scenario is if L is a number less than 1, so very often it will come out to 0 for whatever reason, which would count here. So if it comes out less than 1, then your series converges and you're done. If it comes out to a number greater than 1, your series diverges and you're done. And then the only way the test is inconclusive after you've computed that limit is if the L comes out to be exactly 1. Alright, so feel free to pause this video, take all the time you need to copy down this test. But we're going to jump straight into a couple of examples now. Alright, so our first example series is going to be the sum from n equals 0 to infinity of 2 to the n over n factorial. And I'll use this time to remind you, of course, that 0 factorial is defined to be 1, so it actually is okay to plug in 0 to this series. I'm good there. Okay, so this is a really great candidate for the ratio test, and we're going to find through a lot of these examples that the factorial is kind of a dead giveaway, that the ratio test is a really good choice. So we're going to see a lot of examples with that factorial in this section. Okay. So all of these terms are positive, right? 2 to the whatever is positive, all the factorials are positive, so we definitely fit this description. So what we want to do now is compute the limit of the ratio of consecutive terms. So this one I'm going to spell out really carefully here, just so that it's clear where each of these values is coming from. So my a sub n, the denominator here, is just exactly this formula here. No funny business there. And then a n plus 1, this is going to be this formula, but everywhere I see n, I'm going to write n plus 1, and that requires parentheses sometimes, kind of depending on what this formula looks like. So I'm going to have, instead of 2 to the n plus 1, and then on the bottom, instead of n factorial, it'll be n plus 1 factorial. So it's the factorial of like the next n value. So for something like this in the denominator, I absolutely needed that set of parentheses here to make it clear that the number n plus 1 is what's in that factorial. Okay, so there's no real simplifying or anything I can do here. So what I'm going to do is set up this limit. So I have the limit as n approaches infinity of an plus 1 over an. And we've already done some of this work. So we'll have 2 to the n plus 1 over n plus 1 factorial. That's my an. And it's going to be divided by, or sorry, that's my an plus 1. It's going to be divided by an. So that's 2 to the n over n factorial. And this is really similar to the limit comparison test, particularly our next few kind of computations here, right? You have a fraction divided by a fraction. So we're going to kind of use that same strategy from last time where we multiply by the reciprocal of this denominator, just so that there's like less fractions going on, and we'll see how much we can actually cancel. All right, so I'm going to have my numerator times the reciprocal of this denominator, right? So it's going to be n factorial on top, 2 to the n on the bottom. And so we have some good things and some bad things happening here. So notice for one that because the factorial is involved, we're not actually going to switch to thinking about the continuous version. L'Hopital's rule is kind of out the window because that factorial kind of, you can only plug in integers, so there is no like smooth function version of it. But we can do a lot of simplifying here, and it's going to be enough to actually allow us to compute this limit. So first notice the 2's. We have 2 to the n plus 1 here and 2 to the n here. And there's a bunch of different ways to see this cancellation happening. So you might realize that there's n 2's being multiplied down here. And then there's just as many, but 1 extra times 2 up here. So if this is like 2 to the 10, this is 2 to the 11, right? So this has 1 extra 2. So they're going to cancel so that there's just a 2 left here, and there's just a 1 left on the bottom. It totally cancels out. If that cancellation feels a little bit awkward to you, another way to kind of see this a little more concretely is to use exponent rules. So if you have 2 to the n plus 1 over 2 to the n, you would subtract those exponents. So it's 2 raised to the n plus 1 minus n. And then the n plus 1 minus n gives you that 2 to the 1 power here. Okay, so we also have cancellation with the factorials. And we're going to see stuff like this a lot in this section, so we'll kind of start to get the hang of it. So this n factorial is n times the number before it, times the number before it, right, all the way down to times 2 times 1. This is that same group of numbers, but then it's times n plus 1 as well. So for example, let's say you have 5 factorial and 4 factorial, right? So this is these two values here if n is 4, right? So I have 4 factorial here and a 5 factorial there. 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So see how they have everything in common. It's just that 5 factorial has a times 5 that would have lasted. And that's the case in general anytime these are two consecutive numbers, which they would have to be. So this one will totally cancel with this one, and then all that's left down here is n plus 1. For the same reason that this 5 would have been left over down there. This is the n plus 1 value. So you can use this as a rule in the future if you find that easier. So if you're ever in the scenario where you have n factorial over n plus 1 factorial, that would cancel to just 1 over n plus 1. We'll see that, and we'll see things kind of similar to that frequently in this section. Okay, so let's rewrite our limit with what is left after all this cancellation. All right, so on the top I have a 2 from here, and then this whole thing canceled, so it's just 2 times 1. And then down here, the n plus 1 survived, and then nothing else down there. So all that's left is 2 over n plus 1, and of course, as n approaches infinity, this is 2 over infinitely large numbers, so this limit is 0. Okay, so now let's kind of scoot down here, and we can see our ratio test again. 0 is the L, the capital L from this theorem. So if we go up here, L is less than 1 for sure, right, because we have 0. So our series converges. So we are going to conclude that our series is convergent. Oops, there we go. Now it's on the screen. So our series here is convergent that we started with. Notice that if we had been doing the limit comparison test and we had gotten a 0 at the end, that's an inconclusive case for the limit comparison test. But here the rules are different because you're computing a different limit, right? We're not comparing to anything. We're just comparing the ratio of consecutive terms. So the fact that it comes out 0 here is actually just fine. It gives us an answer. and we're good to go. Alright, so I do have one more example here that I'm going to do in this video. It'll be a little bit longer than a normal video, but I want to point out before we keep going roughly why the ratio test is true. And the way I like to think about it is to think, what if I did this with a geometric series? If I took the ratio of consecutive terms for a geometric series. We're not actually going to define one, we'll just think, okay, usually we have k and k plus 1 for geometric, so we'll keep it that way. So we would have had a times r to the k plus 1 over a times r to the k. Those are like consecutive terms for geometric series. And we have a ton of cancellation. The a's go away. There's one more r up here than down here. So this cancels to just one plain r. Okay, so our limit would have come out to exactly the r value, right? We have the limit of a constant, so that constant would be our answer. And notice that the rules for a geometric series converging are that if this comes out less than 1, you're convergent, greater than 1, you're divergent. That's exactly the rules here. So what the ratio test is doing is comparing your series to a geometric one in general and saying, okay, do the terms go down to 0 as fast as a geometric series? Is it faster? Is it slower? If it's slower than a geometric series, we would have said diverge. And then this case is like the borderline case. Anyway, so that's why I like to think that, or at least kind of how I justify the ratio test in my head, that it kind of is echoing the rules for a geometric series. Okay, so the second series that we will use in this video is the sum from k equals 1 to infinity. And I'm switching to k on purpose so that we get the hang of using whatever letter is there. And our formula will be 3 to the k power divided by k cubed. So this is one, we still just want to decide converge or diverge, and if you actually have a different perspective on this, you could actually prove that these terms don't go to 0. So you could use the nth term test to say this diverges, but it's also a really nice candidate for the ratio test. Okay, so for my ratio test, I do just want to double check that all these terms are positive, which they are. So we're going to jump right into our limit. So I'm going to have k go to infinity instead of n, because k is my letter, but it'll all work the same way. So I'm going to want the k plus 1 term over the k term. And it's important that the k plus 1 term is on top and the k term is on the bottom. Otherwise, the rules that we have for this test don't work. So always be careful that the higher term is on the top. Okay, so I'm going to have 3 to the k plus 1 divided by k plus 1 cubed. That's my k plus 1 term. And then on the bottom, I have exactly the formula from the series. So 3 to the k over k cubed. And I'm immediately going to do the multiply by the reciprocal of the denominator thing because this is really gross to look at. And in fact, the line that I'm writing right now can be your first line if you're comfortable with all of these steps. So my numerator is 3 to the k plus 1 over k plus 1 cubed. And we'll have times the reciprocal of this denominator, so k cubed on top, and then 3 to the k on the bottom. Okay, and then just like the last one, we don't have a factorial in this case, but we do still have a lot of cancellation in a similar way, or at least a little cancellation. So 3 to the k plus 1 and 3 to the k. There's one more times 3 up here than down there, or you could see it as subtracting those exponents, but you get a 3 left over on the top. Now, the k cubed and the k plus 1 cubed, they can't actually cancel. They don't perfectly cancel. There are a few options about how you can kind of mash them together to get to your final answer, and we'll explore a couple of them in the next step, but there's no actual cancellation I can do here, because that k plus 1 is trapped in those parentheses. Okay, so we will get 3k cubed on top and then k plus 1 cubed on the bottom, and everything else is gone now. Alright, so here are a couple different ways. I think there's, I don't know, at least to me there's two different ways to kind of see what we're looking at here. This limit is going to come out to be 3. So if that's what your instincts are telling you, you're in the right direction. So here's one option that you could do. You could realize that what you're looking at is a rational function, right? You have a polynomial up here and a polynomial down there. It's just that down here it's in factored form instead of spelled out. So if you think about actually expanding this is what k plus 1 cubed multiplies out to. And the exact value of that is not super important. All you need to realize is that it starts with k cubed, right? Because then you can do your leading terms trick. 3k cubed over k cubed would give you 3. You could also do L'Hopital's rule a bunch of times to get to that 3, but either way there. If you don't like that expansion, another thing you could do is rewrite, because the k and the k plus 1 have the same exponent, I could also write it like this, right? So I have k cubed on top, k plus 1 cubed on the bottom, and that's exactly what's happening here. And we could say, oh, well, this clearly goes to 1, right? So this goes to 3 times 1 cubed. So a couple different paths to the same place, but they should all lead to the number 3. So here my L, my capital L from the ratio test is 3. Because that's greater than 1, I'm going to say that my series diverges as my final answer here. Alright, that's the end of the video. I'll see you in class.